Assistant Professor of Mathematics at Rutgers University. He completed her PhD in 2016 with Dimitri Gradentosh back at CMU and served as an NSF postdoc fellow at the University of Texas at Austin and Rutgers from 2016 to 2018. Kim is interested in stochastic control and stochastic analysis questions that arise from financial economics. Her current interests include studying systems and equations related to financial equilibrium, especially in the presence of frictions. Kim, the floor is yours.
Okay, thank you. And thanks for the invitation. It's nice to be here surrounded by people. So today I'm going to talk about an equilibrium model with limited participation. I'm interested in equilibrium models because equilibrium models are a way to tell us, or at least to answer a question of what models make good models for asset prices. And so one such answer for this question is good models are those that are formed as outputs of an equilibrium. So when you have a supply curve that meets a demand curve, then they form prices when, well, you can somehow cross them in the middle and prices form from here. So the type of equilibrium that I'm going to be looking at today is called a limited participation equilibrium. And a limited participation equilibrium, the idea is that some market participants have more access to the market than others. So you or I walking off the street don't have nearly the same access as a trader sitting down at JP Morgan with. And so this is the rough idea that's going on here. Equilibrium models with some sort of financial market in the background, they tend to be somewhat easy to calculate or easy to solve, easy to prove existence if you have a complete market. And so if you can trade all of the risk that's available in a market, then you can use tools that aren't available if you have an incomplete setting. And these tools allow you to come up with asset price models in a not so difficult fashion. In a limited participation economy, we don't have this complete market assumption sitting around because some of our agents are limited and they're not able to trade some of the risk available. And so we're necessarily in an incomplete market setting. This is going to complicate things in terms of proving existence of an equilibrium. And so this is the name of the game for me. I want to try to set up a model that has this limited participation feature and then prove the existence of such an equilibrium. And this is going to give us an idea of then what models make good models for asset prices, at least in this specific kind of setting. And feel free to stop me at any point. Okay. So I'm not the first person to take a look at this kind of problem. And so I want to talk a little bit about the problem history. This problem goes back 20, 25 years. And the original work was by Weston in 1998. And so what they took a look at was somehow the most basic of these models where you could say something interesting. So their setting took a look at a time horizon that was finite, so 0 to t, and they allowed for running consumption. They had two assets, a bank account. The bank account was in 0 net supply, but it had an interest rate R. And the stock was in 1 net supply, and they took a look at a stock that was paying dividends at a rate of geometric Brownian motion per unit time. So these were the two assets available in the economy. And they also had two investors, or maybe we could think of this as two classes of investors. Their two investors were an unconstrained agent. The unconstrained agent was able to access both the bank and the stock. And the stock was driven by this geometric Brownian motion rate of dividends. And so this had 1 Brownian motion worth of noise. This agent could access 2 securities. And so this agent was going to face a complete market in his problem. Then there was a constrained agent. And this constrained agent was only able to trade in the bank account and consume. So the question that the Fukuoka looked at was, well, does an equilibrium exist in this setting? And if so, what happens to equilibrium prices? How do they compare to this Pareto efficient case? So this is the Pareto efficient case. This is going to be our complete market case. So if both agents had access to everything, they would face complete markets. And then how do prices in a limited participation economy compare to that case? So this problem, it looks in a way to be deceptively simple. The setting has one Brownian motion. It's a geometric Brownian motion per rate of time dividend stream that's coming out. It's not like this is some complicated Markov process or any sort of, there's no SDE that's very complicated here. It's a stock in a bank account, and the stock looks an awfully lot like a geometric Brownian motion. And so what's the complication in a model like this? The complication, believe it or not, comes in through this constrained agent. The constrained agent has a problem that also sounds deceptively simple. This agent has two choices in this world. Either put your money in the bank account and wait until a later period, or consume right now. And by the end of the time period at capital T, all of the consumption is going to have happened for the model. You're going to want to run out of everything by the end of the time. So how do you divvy up your consumption versus placing your money in the bank account till later optimally? This doesn't sound like a very difficult problem. What makes it difficult is the fact that we have an interest rate R for our bank account, and this interest rate is determined in equilibrium. So we don't get to pick this. This is something that's an output of equilibrium. And when it's an output of equilibrium, we can't just say, let's let this interest rate be zero, or let's let it be constant or deterministic. This is going to be determined in equilibrium. And when it happens in equilibrium, it's going to be stochastic. As soon as it's stochastic, this question that the constraint agent's going to face of, do I just stick my money in the bank or do I consume? This becomes very complicated mathematically very quickly. And so what did Bassak and Cuoco do in order to try to rectify this, in order to try to prove existence of some sort? What they did was they assumed that the constrained investor has logarithmic preferences. So his preferences are described by a log utility function. And yeah, you're shaking your head. Sorry.
Because he and I, we're working on that.
Okay, yeah.
Okay.
With a stochastic interest rate, or?
No, with
Okay. Okay. Yeah. So I mean, then you know that when you have logarithmic preferences, a lot of nice things happen. In this problem, it seems like a lot of the nice things happen with the logarithmic preferences, because when you have your optimization problem, your first order condition takes the derivative of your log function and you get just 1 over x as the derivative of log of x. And so this makes this constrained investor's problem nice. And it really simplifies it. You still have these stochastic interest rates to deal with, but they're manageable when you have the log investor for the constrained agent. So what Bassak and Cuoco did in their 98 paper was they were able to prove the existence of an equilibrium where both of our investors would have logarithmic preferences. So we have a log constrained and a log unconstrained. Okay, so this paper, this was from back in the late 90s, and this has continued to be of interest even until today. And so what have people done since then? So since then, Julian Cubinier had a paper that came out in 2012. He was not really moving beyond the Bassak and Cuoco framework in terms of these logarithmic preferences, but he was interested in something a little bit different. What he was interested in is that in the Bassak and Cuoco paper, it actually turns out that there are bubbles in equilibrium. And this is sort of a fascinating thing to study and observe. So what happens is there's some equilibrium stock price S. And this is described in terms of some kind of dynamics, some sort of Ito process. You can figure out what is the stock price in equilibrium. And then you can ask the question, how much does it cost to replicate the payoff of this stock? And so you get a formula that's something like this. D is the dividend stream that the stock is going to pay out. And then these C's, these are a state price density. So there's a discount factor in there and a market price of risk. This is really looking at some expectation of the dividend stream discounted under a risk neutral measure. And so what he was able to see was that the stock price in equilibrium was actually strictly bigger than the amount that was needed to replicate somewhere along the way. And we're going to see this in a few slides in this model. There's a property where you need somehow discounted stock prices under a risk neutral measure adjusted for dividends is a local martingale. And in fact, it ended up being a strict local martingale here and not a true martingale. And so you get this strict inequality.
But the side is a mark,
Okay, so the left-hand side here, so there's a little t sitting inside this conditional expectation, so it's not. But let me maybe write down. Let me write down what is supposed to be a martingale. So what should be a martingale would be, you look at the dynamics of a stake price deflator times a stock price, and then you have to adjust it by the dividends. So this is, in general, a local martingale. And in the model of the Sacco-Cuoco, it turns out that this is a strict local martingale. And so with this strict local martingale property, then this conditional expectation, well, you get a strict inequality between that and the equilibrium stock price. So this is something that, in the end, whenever I show you what I've done with this model, we're going to ask the same question too. In the model that I do, it's not going to be so interesting. It's going to end up that everything that we want to be a martingale is a martingale. But this was something that was studied, and I mentioned this mostly because the Sacco-Cuoco, this goes back for a long time, and it's something that really has been interesting to a lot of people. So this is something where they looked at a model where both agents had logarithmic preferences, and this was very simple in a way, but somehow that's not a knock against this paper. This is really to say this paper was the first of its kind, and it was simple, but it was also very interesting, and a lot of people took interest in it and were able to ask a lot of different questions. And so this was an interesting phenomenon that came out of this work. This logarithmic preferences, though, is really pervasive, and it's difficult to get around. So there was a working paper by Prieto in 2013 who looked at trying to extend beyond both investors having logarithmic preferences. He was able to move so the constrained agent was still logarithmic. The unconstrained agent is able to be a power investor. So his preferences are described by power utility. And what he had to give up to do this is that he had to move to an infinite time horizon. But okay, so he did that, and he was at least able to get to a power investor of some sort. You want to see an example of how this problem can get complicated very quickly. Chavakari's paper in 2015 is where to go. So he tried to look at both agents being power investors, and in the end, the equations that are here, they're just complicated, and there's no resolution in terms of if equilibrium exists. It's really unclear if such a thing is going to work. And so what I want to have a look at is try to set up this model in a way where we can move beyond this log investor for the constrained agent. See if there's a way to do that. So the last reference that I have written here, this doesn't directly apply to this limited participation framework, but I mention it because any sort of contribution to this limited participation framework is also going to be a contribution to an equilibrium with stochastic interest rates. And so an interest rate in an equilibrium model, the way we think about this is interest rates are what tells us how much we care about consuming today versus how much we care about consuming in the future. That's measured through an interest rate, and stochastic interest rates in incomplete equilibria are very difficult to establish. And so the only two examples I know in at least continuous time are the Sacco-Cuoco 98 paper, and then this paper by Christensen and Larson in 2014. And so they were looking at stochastic interest rates that were coming from a stochastic income stream. And they were able to prove existence in a model where they could actually write things down pretty explicitly. And so I mentioned this because these stochastic interest rates really just complicate the situation. This is what makes this limited participation problem so difficult, even for this constrained investor that has very few choices in this world. It's still so tough. And so what I'm going to show today is also going to be a contribution to this stochastic interest rates literature in an equilibrium setting. Okay, so how do we get around this log investor? Or how do we move beyond it? The difficulty with this problem is that it's hard to even write down a system of equations that you can solve. And so a big contribution of what I'm going to show you today is just the fact that we can write down equations. And just to be able to do that is already more than what's been done in a lot of cases for this problem. So how do we write down these equations? This goes back to a paper that I worked with Gordon Zikovich a few years ago. And when we were looking at a different problem, but we were also looking at an equilibrium problem. And we wanted to have this running consumption feature. And we found a certain variable reduction that would really help us write down our value function nicely and then be able to get some equations. And so we're going to try to use that trick here. And so there are three ingredients that we need in order to make this work. The first of these ingredients is that we need some kind of Markov structure in the background. That for us is going to be a Brownian motion. That's B. And B is one-dimensional. It's nothing fancy. We could make it more complicated and still get this variable reduction to work, but it works with a one-dimensional Brownian motion. So we're going to do that. The second feature that we need in order to get this to work is that we need to use exponential utility functions. So our agents are going to have preferences described by these exponential type preferences. And with this is a key feature in what we need to get this variable reduction. The last thing that we need is that we need to assume that there is a traded annuity in the market. So there can be as many assets as we want to get this variable reduction to work, but one of them better be an annuity. An annuity is a security that pays off a dividend of 1 per unit time. We have a finite time horizon model, and we're going to set it's also going to pay off a dividend of 1 at the terminal time too. But annuities are securities that pay off a unit dividend stream per unit time. And so we need to have one of these in our market in order to trade, in order to get our variable reduction. So then what is this variable reduction that we get? This is a little bit loose here because I haven't actually told you what a lot of these symbols mean, but let's work through it. The little v, this is representing our value function. So this is our maximum over some optimal consumption streams that we could choose from of expected utility of running consumption and a terminal well. This is going to be a function of time, our dividends paid out, D. These are going to be dividends for our stock. This is going to be really just our underlying Markov process that we're interested in. And then our wealth X. Our value function is a function of these things. And then we have the following decomposition. We have minus E to the minus our risk aversion times X discounted by our annuity, and then plus some sort of certainty equivalent leftover term. And then this leftover term, this is a function of T and D. It's not a function of our wealth X. So this is really the key feature. And in the end, our annuity is also going to be able to be written as a function of T and DT. And so this is a nice feature as well. And what's going to end up happening is that the annuity itself has some kind of Feynman-Katz representation that'll provide us one equation in a system of equations to solve. These G functions, these are going to provide us with some other equation in a system of equations to solve. And all of these things put together will give us a system that will then describe our equilibrium. And so if we can solve this system, then we can get at our equilibrium.
So is the thinking that there's two assets trading, one being stock with a dividend, the other being an annuity?
That's it exactly.
Okay.
Yeah. Yeah. So what we're going to do, I think this is the next slide. Yeah. So what I want to do is then set ourselves up in a model where we can try to move beyond this log investor. And the way that we can do that is by moving to look at two different exponential investors. And then what we have is we have our two traded securities where now instead of a bank and a stock, we have an annuity and a stock. And so we have our annuity, it has its constant dividend stream. We have our stock, it has some dividend stream D. I write here, D is going to look like, this is some solution to an SDE. This is going to give us our Markov structure. And so these are our two traded securities.
Yeah. So I have a question.
Yeah.
So D I know is an exogenous process. And say, so I know, for example, if D were just constant and positive, then this S process is being driven down from, let's say, a positive level. And it hits zero, I think. And but I might be wrong. And there's something happening that's hit zero. Well,
Let's see. So you're saying this is the case where we don't even really have a Brownian motion coming into play. D is just happening through its
yeah. So
drift.
yeah. So I'm just thinking of a special case of what you're thinking about. But so I'm actually saying, what if mu D was zero, sigma D were zero, and so that means D a little b is zero, and that means capital D is constant, and let's say positive constant. Like I don't know if you're worried about limited liability or not. As I guess what I'm really saying.
Yeah. So I'm not really thinking of it in those terms. This should be okay to think about it like that, right? So I guess my concern is if we don't have this Brownian motion coming into play in our dividend stream, then our S is not really so different from our annuity itself.
That would be true.
And so in equilibrium, we're not going to have any sort of volatility terms anywhere. These are all going to be zero in equilibrium.
Yeah. Okay, so maybe that's too weird what I said. Let me just, what I'm really wondering is, so now let's say maybe it's not zero, let's see what you're thinking. And what I'm really wondering though is if D were say a positive stochastic process, then I'm seeing that the way it's entering the stock price is negative. The positive B process is driving us down.
Yeah.
And I'm just wondering if you're doing anything special at zero or just letting us go negative at zero.
So S can go negative.
Okay.
Yeah, and
Okay.
this is one of the drawbacks of exponential utility functions, because exponential utility functions, right? If we had a log investor or we had a power investor, there'd be this sharp divide happening at zero. We'd have the Anata conditions that would tell us that we really we can't go negative. We'd have a minus infinity utility of negative. Well,
Okay.
and then we would also have, right, at zero, the Anata conditions would drive us so that we don't ever want to hit zero in terms of our wealth. And okay, this isn't exactly wealth, this is the
Yeah, I
stock,
mean, so that's,
but
like, let's say if I was trying to map to the real world, then S, I wouldn't map it to a stock, because I think the stocks is not negative. So I'd have to say, now I have to swap or something like that. Positive. So that's fine.
yeah. So I guess what I want to say out of this wealth being negative or not business is exponential preferences. They work really well with additive type things.
Yes.
And so this form is much more of the spirit of additive type things.
Sort of a mix, right? I mean,
Yeah.
I see why you say additive, especially the dividend part. But there's also a geometric aspect because you have mu A times S.
Yeah. And these are here because this just works out nicely with some of the equations that are to come. But
Okay.
yeah, there's a little bit of this geometric business. But yeah, S is mostly an additive
Okay,
type element.
okay.
Okay, so yeah, so what we're going to take a look at is two investors that have exponential preferences. We have two traded securities, but now instead of a bank, one of them is this annuity. And so our first investor, this is the unconstrained investor. This agent is able to access both the stock and the annuity. So ultimately, this agent is going to face a complete market. And then we have investor two. This is the constrained investor, and this investor can only trade in the annuity. So this agent's choices are either put your consumption good into the annuity and then wait until some future time, or consume right now. And so that's this agent's choice problem. It's a little bit different from the choice problem of the Bassak and Cuoco type of limited participation economy, because annuities, they can have volatility. And so they have a drift, they have a volatility. If the volatility is zero, then the drift of the annuity is the interest rate, but it's not quite like a bank account. The annuity doesn't replicate a bank account unless the volatility of it is zero. However, the first investor is going to face this complete market. And so this agent is going to be able to replicate a locally riskless security. So we're still going to be able to determine some kind of stochastic interest rate in equilibrium out of this model. This is at least something that I'm interested in doing, but this is really just the mathematician in me gets interested in this. All right, so how do we define equilibrium? Maybe first, how we define the agent's optimization problems. They're going to be looking at an optimization problem for running consumption and terminal wealth. These rows that are in here, this is just the time preference parameter. And so they're maximizing over consumption stream C. Theta is their holdings in the annuity, and this psi is the holdings in the stock. And then psi 1 is something that's free to determine, but psi 2 is going to be just identically zero because agent number 2 is constrained and can't access the stock. So equilibrium, what does equilibrium mean? Equilibrium is going to consist of optimal trading strategies and optimal consumption streams, and then dynamics, so wealth, or not wealth dynamics, for dynamics for our assets, such that the trading strategies are optimal for their investment problems. And then market clearing happens. And so market clearing is going to tell us this is where our supply curve meets our demand curve, and we form prices. So we need that, add up all of the consumption in the economy. This better equal all of the supply in the economy, which is equal to the dividends of the stock plus the dividends of the annuity. Then we also need that the total number of shares in the annuity is equal to 1. And the total number of shares in the stock is equal to 1, but this guy is constrained. So we just need that agent 1 is going to optimally choose to hold 1 share of stock. So this is equilibrium. Now what we want to do is try to make use of this variable reduction in order to write down some system of equations that we could solve, and then this system of equations could hopefully tell us what are all of these parameters. Okay. One more thing before I tell you what the system of equations is. So now the thought is, how do we get there? And ultimately, this just involves calculating a lot of dynamics and setting some dt terms equal to other dt terms and setting some db terms equal to other db terms. But it has to be done in a smart enough way. And so what happens is any term that's not a wealth, we're going to be using this variable reduction. And so it's going to be a function of time and then our dividend stream for the stock D. That's going to be our underlying Markov structure that we use. Then we look at agent 1. Investor 1 is unconstrained, is going to face this complete market. And so we write down his state price deflated. So this is going to have a discount factor R, and then we're going to have our market price of risk kappa sitting inside a state price deflator, we're going to use the first order condition for his optimization problem. That tells us that e to the minus risk aversion times our consumption is proportional to this state price deflator. And so then what we do is we say, okay, well, I know that my assets, if I discount them and look at them under my risk neutral measure, I should get martingales when I adjust for the dividends. That's what this is telling us here. We look at these dynamics. This is our annuity dynamics discounted under some risk neutral measure. These are our stock price dynamics discounted under a risk neutral measure. I should say the risk neutral measure, because this is going to be a complete market when we're looking at agent one. These are going to be local martingales, so we can calculate DT terms, calculate DB terms, set our DT terms equal to 0. And then if we use our clearing conditions, we can generate enough equations that we can finally get a system to really describe equilibrium. So here's our system of equations. It looks like a bit of a mess, but it's two equations. It's written in terms of a BSDE system. It can also be written in terms of a PDE system. The reason I write it like this is because the existence result that I'm going to use is involves BSDE systems. So that's what we're going to do here. Some key features. This little a is going to be the log of our annuity. And this Y2, this is going to be agent 2's certainty equivalent type term. That's going to be this term that breaks out in our value function reduction. And so these things are coupled. They're coupled through the annuity. So e to the minus a, this is like a 1 divided by the actual annuity. This turns up here. This also turns up here. And so a is in both of these equations. We also have quadratic terms. So these terms that are sitting in front of the DB, these are like the first spatial derivative that appears in a PDE. And so this first spatial derivative in our PDEs that we have, they show up in both of these equations. So Z2 shows up in our equation for Y in two different places, and it shows up quadratically. A shows up quadratically also, or sorry, the first spatial derivative of A is going to be this sigma A. That shows up quadratically in the A equation. So these are kind of, these are a bit nasty, and they're fully coupled, and they have these quadratic terms in our first spatial derivative type terms or our DB terms, however we do this. And so then the question is, how do we come up with a solution for this?
Did you say sigma A enters quadratically? I'm not seeing that.
Oh yeah, it's in here. So there's a square outside of all of this. And
I see it. Sorry.
yeah.
Okay, yeah.
Yeah,
Right.
so these are,
You're right. Okay,
yeah,
sorry.
this is our system, and it's nice that it only has two equations in it, but they're coupled in a somewhat nasty way. Once we figure out the solution to this, so suppose we have a solution, then we can figure out the other terms in our equilibrium based on that. And so I write a couple of them here. Our annuity is this e to the little a from our equations. This alpha sum, I write this as an aggregate risk aversion, and that pops up in a few different places. So we have equations for what our interest rate and what our market price of risk look like.
Okay, and are there sign constraints on either the interest rate or the market price of risk?
No,
Okay.
no. I'm going to show you an example at the end, and we'll see in an explicit case what can be said about these. And actually, it turns out that the interest rate in this case is going to end up even being negative.
Okay.
But okay, these are also just more terms that we can determine based on the system of equations. And the form of these themselves isn't necessarily that interesting. It's more just to say, once we have a solution to this BSDE system, how do we figure out all of the other terms in our equilibrium? And so this is what we can figure out. Our kappa, our R, and our mu A, our drift of the annuity, we can figure out pretty easily from our BSDE system. To get our stock price dynamics, that's going to involve our sigma S and our mu S. That takes a little bit more work. It's going to involve another BSDE, but this BSDE is not coupled. Once we know the solution to the first BSDE, we can fill in those terms, and this one is only going to be linear in the Z1 term, so it ends up being nicer. I think this is where the Z1 shows up here. So this looks long and it involves a lot, but this one is solvable as soon as we know what the solution to the first system is. So if we have the solution to the system, we get all of our equilibrium parameters that we're going to want. And we can also describe our optimal wealths and our optimal consumptions in terms of these things, but those aren't quite as interesting as our dynamics. So the result then is that a solution exists to this system. The specific type of solution that we're going to get. And so I list some sort of assumptions here that are coming in. The mu D and sigma D, these are our dynamics of the dividend of the stock. So we have to make some assumptions in order to assume, or in order to ensure that this is going to be a unique, strong solution to the SDE for the dividends. And then along with that, we're relying on some existence results from BSDE theory that are going to require certain boundedness conditions. Once we do that, then we get a solution to this BSDE system. It's an S infinity cross BMO solution. That's going to mean that S infinity means uniformly bounded. So A and Y2 are going to be uniformly bounded, which is nice. And then little BMO means that this integral sigma A dB and Z2 dB, that this is going to be a BMO martingale, which is a very nice class of martingales. You get a lot of nice integrability by knowing that you're sitting in BMO. Okay, I don't want to say too much about the idea of the proof. I think we're getting a little bit in the late stages of the talk. But basically what this boils down to is really trying to cram this into some sort of existing BSDE result. And it doesn't really fit so nicely, but with not doing too much to it, you can kind of get it to work. And so specifically, there's a paper by Hao Xing and Gordon Zikovich from a few years ago that looks at these couple systems of quadratic BSDE. And what they found was that there's a specific structure condition to the quadratic nature of these coupled systems that's really important for trying to prove existence. And as it turns out, we have that specific structure in this system, which is really some kind of quadratic, or not, some kind of triangular dependence and a quadratic. So what that's meaning for us is in our equation for A, we have quadratic dependence on both sigma and Z2. But in our equation for Y2, we only have quadratic dependence on this Z2. And this is what allows us to get our way into this Xing and Zikovich.
I just have a question about
Yeah.
your assumptions. So regarding utility functions, I know, is it that both investors have exponential utility?
Yeah, both investors have exponential utility. They can have different risk aversions,
Okay,
but they're both that same structure. They're both exponentials.
okay, thank you.
Yeah, and that's these alpha parameters. So alpha 1 and alpha 2 are their risk aversions, and then alpha sum is somehow an aggregate risk aversion.
Thank you.
Yeah. All right, so this is the idea of how to get this existence result. Once we have this existence result, it's really plug and chug through some formulas to see what all of the parameters are that we're interested in for dynamics. Okay, so maybe a simple case just to look at. We can solve this in some simple cases. And this is one that's simple enough that we can write down formulas. We don't even have randomness sitting inside our market price of risk and our interest rate. And yet we can, it's nice to be able to just write down an example that comes out of this framework that's not a huge mess. And so this example is going to look at the dividend process that's just Brownian motion. So the stock pays off a one-dimensional Brownian motion dividend. And in this case, we end up with our volatility of the annuity is 0. So then our drift of the annuity is the interest rate. And so that means that our annuity, it's not exactly a bank account, but it can replicate a bank account because we have our annuity dynamics plus the dividend stream for them. It's just the interest rate times the annuity to T. And then it pays off this terminal dividend of 1. The stock price has these dynamics. This can be solved for explicitly. And so this is pretty nice to have this explicit representation. And our interest rate and our market price of risk can be written down explicitly too. And so these are written down in terms of some kind of market parameters. This rho is some kind of aggregate time preference parameter. The formula for it is here. It's not so interesting. Yeah, so the meaning of the row 1 and the row 2, those are time preference parameters. So they show up in the utility function or in the optimization problem. Those are these things. Yeah. Yeah, time preference parameter. And here, I mean, it's a finite time horizon, so it's not really very crucial to have this time preference parameter, but we could write it in there. So I included it because it's possible, but mathematically, it's not really necessary.
I have a question about the stochastic process for the I like your example where the sigma A is 0. I mean, that makes sense to me. What doesn't make sense to me is sigma A is not 0. Because, like, I'm understanding the claim that's getting $1 per instant and has a flat payoff. And so it's not by nature all that different from a money market account. It differs because it's getting that $1 per instant. And like the money market account its sigma M equals 0. So why does the annuity not?
So I think it's maybe easier to think about an annuity as it's related to something like a 0 coupon bond versus an annuity as it's related to a bank account. So a 0 coupon bond, this is something that pays off 1 at some terminal time.
Yeah.
But we know that a 0 coupon bond has volatility throughout our time between now and maturity. And so this is a similar thing. And an annuity is really, it's pretty similar to a 0 coupon bond. It's just, it pays off this terminal dividend of 1, but it also has this running dividend going on in the inner.
Coupon bond.
Yeah, I guess it's a coupon bond. Yeah, exactly. Yeah.
Okay, that's good.
Yeah, I guess I shouldn't even compare it to a 0 coupon bond. We should just call it a coupon bond.
Yeah.
Yeah.
And okay, I see what you're calling it. Okay, so you answered my question.
Okay, yeah, yeah. So then in this example, excuse me, in this example, it's as if we're thinking about a coupon bond or a 0 coupon bond where we have a deterministic or a constant interest rate, in which case, if we're going to sit there and try to compute risk neutral expectations of a terminal payoff of 1 that's discounted, we're going to get a coupon bond that has 0 volatility.
Yeah.
Right. If we're sitting in a deterministic interest rate model, then calculating these fixed income security type calculations, it's going to work out nicely for us. And that's what's happening. That's what's happening in this example.
Okay.
Yeah. So maybe just to have a look at what we get out of a model like this in this example case, it's interesting to compare what we have to this Pareto efficiency. So what happens in a complete market? If both agents have access to both assets, then they're both going to face a complete market. Prices are going to form in a different way because they both have access to all of the risk in the market now. And so we can say what happens to our market price of risk in our model versus the complete case. And same for the interest rate. And so for here, what we see is what we would really want. Our market price of risk is something that's strictly bigger than the market price of risk in the complete case. And this makes sense because we would expect that if some of the agents in the market are constrained, then we have this unconstrained agent who we need to really entice in order to want to hold this stock. In order to want to invest optimally in the stock as holding all of it, you're going to have to increase the premium somehow in order to get this guy to invest in it. So this is what's being reflected here in this kappa is bigger than the complete case. The interest rate, on the other hand, has more demand for it. People are more interested in stashing money away in some way whenever there's a constraint. And so here,
So,
yeah.
lower the price,
So the constraint is going to, oh, let's see, we have to think about that because it's going to, right, it lowers the interest rate and it increases the premium here, the market price of risk. But then the stock is pinned down at the terminal time. The annuity is pinned down at the terminal time. So then, so let's see, if
So when you say
we,
lowers the price of what?
so it should
Of what?
increase
Of
the
what?
price of the
or
annuity.
stock?
the stock.
Of stock. So stock's real
Yeah.
value, remember? So you may be thinking the stock is being positive in value. Okay, so you know,
Let's
if
see.
we're changing the discount rate of something to be positive or negative, it's not clear to me what the impact is on the price.
Yeah. Yeah, I'm actually not sure. And this is a good question. And it's, what's confusing is here we have, oh wait a second.
One is
Um,
constrained, the other is to hold more of the stock, and so it increases, and that makes sense. Both for all people, for all the stock that is produced back.
Yeah, yeah. So yeah, I think it will decrease the price.
So here's another question. So this Pareto efficient case, you must have redone the whole problem to remove the one constraint that the holding in the stock by the what was previously the constrained investor. Is that what you mean by?
Yeah, yeah. So you remove the constraint. So both agents are able to access the bank and the stock.
Yeah.
And
yeah,
so-
annuity and stuff.
And so, yeah, oh, sorry, yeah, the annuity and the stock. And so they only differ in their risk aversion parameters.
Okay.
And so then solve the problem that way and see what you get in terms of kappa and R.
Okay. Okay, that's good. I mean, so I'm just thinking these results are really nice for like, policy consideration. So, you know,
Yeah,
you can ask questions like, you know, if we open up the stock market to everybody, you know, what will happen to interest rates, for example? And you have an answer to that.
yeah,
Maybe.
yeah, yeah. So I think this is interesting. I think it's interesting from a mathematical perspective because I'm interested in things like these system of equations, but I think it's interesting too from a policy perspective because if you're going to think about the one type of security that the most people in this world have access to, it's going to be some kind of interest paying security. And there are many people that are so constrained that this might be the only access that they have to any kind of financial market. And so this is really a practical consideration to think about. This model is so highly stylized. This is really written just to be able to try to extend one step beyond what's been done before. And this is not anywhere near where it would need to be for a policy. But yeah, I think this is an interesting message. Okay, so from here, I just want to conclude and say what's been done. And so what I do here is set up this limited participation economy in a way that we're able to write down a system of equations that can describe it, and then prove existence of this equilibrium by proving the existence to this system of equations. And so this is a way that we can move beyond this constrained log investor of the original Basov and Cuoco work from 20, 25 years ago, It's also a way that we can see an example of a stochastic interest rate model in equilibrium, in an incomplete equilibrium. It uses this variable reduction with the traded annuity in order to come up with the system of equations. And one thing I didn't really talk so much about, but I just want to mention is that when we look at these exponential investors, this original observation of Huganier from the original work back in the 90s, that there were bubbles in equilibrium, with exponential agents, this sort of problem goes away. These local martingales are actually martingales. They're not strict local martingales. So this is another angle that we can see here as well.
Yeah. So let me say there's even more contributions. So besides going beyond the constrained log investor, I mean, it so happens that the particular utility function you chose, works well with inputs that are real value as opposed to inputs that are strictly positive. Because
Yeah.
for log, we're only going to be a strictly positive quantity. And so that means that, like, if we're trying to apply this to, say, crude oil futures prices, the fact that they go negative, is going to rule out the previous results. And,
Yeah.
But your model comes to the rescue. That's one thing.
This is refreshing because
Okay.
most people really don't like
Yeah,
exponential.
I'm the opposite. But I believe you faced that, but I think you didn't be a little bit at the beginning. But I see the virtue of what you're doing. And the other point I want to make is that example that you showed at the end, just on the previous slide, is really nice, I think, because it's more than just proving existence. You actually spelled out exactly so you constructed the solution as well, right? So
Yeah. I mean, I think you should have an example of anything that you do. And so this is a nice example.
yes, agreed. So yeah.
I think about the kind of segregation that you have wanted to invest, because it's not due to the fact that it's not a self segregation, right? It's, so that you have a participant who would like to participate, but is actually prohibited from participating. While a more general approach would be that you don't have you can't even look at the price that you make.
Oh,
that you
yeah.
made in the market. So they have full information, full approach to the price. They know everything, so they're not limited by any kind of information, right? So it's a kind of situation that has only to do with the regulation that prohibited from trading.
Yeah. So
You don't
I
have a
guess
set decision to stay out.
yeah, I see what you're saying. I think, yeah, so I don't think the way that this is set up, I don't think it can sort of answer what you're trying to suggest. I think because even the constrained agent here doesn't necessarily need to observe the stock price dynamics. He can infer them just because he knows the underlying Markov process, which here is this dividend for the stock. Yeah, so then what would happen if he couldn't observe the dividend for the stock?
The constraint, you don't have to don't have need necessarily to offset the market, the stock and the price of the stock.
So you don't have to observe the price of the stock, but the constrained agent observes the dividend stream for the stock. And so this, I think, is really the same point that you're trying to make is once you observe the dividend stream for the stock, then you can infer what the stock price dynamics are going to be. And so the dynamics of the stock themselves don't really matter. It's more knowing the dividend stream that matters. And the constrained agent, everybody can see it. Yeah. So yeah, there's no hidden information here in some way. And that would be an interesting twist. I wonder if you could get around like a filtering problem with this.
I just have a comment.
Yeah.
So you keep, referring to the dividend process as the Markov process. It is, but it's a very special Markov process. process where there are absolutely no jumps over time. So, maybe you should refer to it as the diffusion process instead. to be more
Yeah.
Precise.
Yeah, sure.
Because that's actually important in your setup. So if the dividends could jump with random jump sizes.
Yeah.
Then the guy who can trade in both the stock and the, he's not facing a complete market. Yeah.
No, well, yeah, no, he isn't. And if there are jumps in this dividend process, then the system of equations that we're going to get out, I don't think there's any hope for solving.
I would refer to it as a diffusion process.
Yeah,
And the letter works really well.
yeah, that's true.
Okay.
Yeah, yeah, so this was all that I wanted to say. Thank you very much.
All right.
And
Thank you.
thank you for your questions.
Well, let's see. Do we get any questions in chat? Zaka, are there any questions or comments in chat? Okay, all right. Okay, we're gonna wrap up. All right, thanks everyone.
Thank you.
Okay.